Ever wondered what actually happens in the split second between pressing enter on google.com and seeing the page appear? Welcome to lesson 2 of our networking journey, Packet Journey, where we'll follow a single packet from your laptop all the way to Google's server, frame by frame. Master this one trip, and every networking topic that comes after it suddenly makes sense. So here's the roadmap for the next few minutes together. We'll trace the complete journey of a packet from your browser to Google's server, breaking down every step along the way. DNS lookups, ARP requests, encapsulation, routing, and decapsulation at the other end. You'll see exactly what changes at each hop and what stays untouched. And by the end, you'll have a mental model that quietly unlocks just about every networking topic you'll ever encounter. So let's set the stage. On one side, your laptop, sitting on a home network with a private IP of 192.168.100, its own hardware MAC address, and a gateway at 192.168.1. That's its doorway to the outside world. On the other side, somewhere across the internet, maybe 10 or 15 hops away, a Google server answering to the IP 1.46. Between those two endpoints, in just a few milliseconds, dozens of things have to happen across multiple devices, layers, and protocols. Master this one journey, and honestly, the rest of the curriculum starts to feel obvious. And our very first problem is that your laptop has no idea what Google.com actually means. Computers don't speak in names, they speak in IP addresses. So, before a single packet of real data can leave your machine, it has to ask a question. Who is Google.com? That's DNS resolution. Your browser checks its cache, the OS checks its cache, and when neither has the answer, the OS fires off a tiny UDP query on port 53 to a configured DNS server. Something like Google's 8.8.8.8. Milliseconds later, the answer comes back. 142.250 to 190.46. The OS tucks that away in its cache, so next time the lookup is instant. Now that your laptop has an IP address to aim at, it faces a quick decision. Is that destination sitting on the same local network or somewhere out there on the wider internet? To find out, it applies the subnet mask to both addresses. Your machine is 168.1.100 on a 24 network, so its network is 192.168.1.0. Google's server lives on 142.1250.190.0. Clearly a different neighborhood. That verdict matters. If the target were local, your laptop would ARP for its MAC and talk to it directly. But since it's remote, the packet gets handed off to the default gateway, your router at 192.168.1.1, to begin its journey outward. So the gateway is the next stop, but knowing its IP isn't enough. To actually place a frame on the wire, your laptop needs the router's MAC address. Enter ARP. Your laptop shouts a broadcast across the local network, addressed to fluff, meaning everyone, asking who has 192.168.11. The router answers back directly, "That's me, and here's my MAC." Your laptop caches that reply so it won't have to ask again. And now, with both the Layer 3 and Layer 2 destinations locked in, it's finally ready to build the frame. And here's where it all comes together. Encapsulation in action. At the core, we've got a TCP header opening the conversation, a random source port, destination 443 for HTTPS, and the SYN flag set to start the handshake. That's wrapped in an IP header carrying your address, and Google's, with a TTL of 64 and protocol TCP, and the whole thing is sealed inside an Ethernet frame addressed from your Mac to the routers. 3 layers, nested like envelopes, ready to hit the wire. That frame now leaves your laptop, hopping over Wi-Fi to the access point, then over Ethernet through the switch until it lands at your home router, and this is where the real work begins. The router strips off that Ethernet header, looks up Google's IP in its routing table, and sees the next hop is your ISP. It decrements the TTL from 64 to 63, a safety net against infinite loops, then performs NAT, rewriting your private source IP into the public WAN address. Finally, it builds a fresh Ethernet header for the next link because those MAC addresses are about to change completely. And that same dance now repeats over and over. Your packet leaves the home router and enters the ISP's edge, then a regional ISP, onto a backbone carrier, across to Google's edge network, through their internal data center routers, and finally to the server itself. At every single hop, the router strips the Ethernet frame, consults its routing table, and rebuilds a fresh header for the next link. Typically, that's 10 to 15 hops, each adding a millisecond or two for a total round trip of 20 to 50 milliseconds across a continent. Finally, our packet arrives at Google's server, where the whole process now plays out in reverse. The server peels off the Ethernet header, then the IP header, reads the TCP layer, spots the SYN flag, and hands things up to the application listening on port 443. It then builds a SYN-ACK reply, wraps it back through every layer, and sends it home, along essentially the same path, through Google's network, across the backbone, back to your ISP, where NAT translates the public IP back to your laptop's 168.1.100. A final ACK from you completes the handshake, and just like that, in one round trip of roughly 20 to 100 milliseconds, a TCP connection is born. Now that we've followed the whole journey, let's freeze frame one critical insight that ties it all together. What actually changes as the packet travels, and what stays the same? The layer 2 frame, those MAC addresses, gets rewritten at every single hop, because MACs only have meaning on one local link. The IP addresses, by contrast, stay end-to-end, with the one exception of NAT at your network's boundary. TTL ticks down by one each hop to prevent loops, but ports and application data ride through completely untouched. That's the secret to how the internet scales. Routers do the minimum work at L2 and leave everything above it alone. So, how long does this entire journey actually take? Let's put numbers on it. DNS lookup runs 10 to 50 milliseconds. ARP just a few. The TCP handshake adds 20 to 100. TLS another 40 to 200. Then the HTTP request and first byte. And finally, rendering, which is often the heaviest slice. Add it all up, and you're looking at roughly 100 to 500 milliseconds from keystroke to visible page. And here's the kicker. On a warm cache with reused connections, you skip most of these steps entirely. That's why your second visit always feels instant. Let's lock this whole journey into one quick reference you can come back to anytime. DNS resolves the name. Your machine checks if the destination is local or needs the gateway. ARP finds the next hop MAC, and your data gets wrapped in Ethernet, IP, and TCP headers. Switches forward by MAC, while routers strip, route, and rebuild across 10 to 15 hops. And remember the golden rule. Layer 2 changes every hop because MACs are local, but Layer 3 IPs stay stable end-to-end while TTL ticks down. And that's the full journey, from a single keystroke to a packet arriving at Google's front door. In the next lesson, we go deeper into encapsulation itself, exactly what each layer wraps around your data on the way out, and how the receiving side peels it all back apart. If this clicked for you, head over to Dargslan.com or the YouTube channel, and I'll see you in Lesson 3.